So what did we do last time? Hopefully we won't have lagging issues. Last time, okay, what did we do? We talked about Mellin transforms. Mellin transforms and inverses. We know the Mellin transform we've been studying for a long time now. We have some kind of character. We integrate over the positive real multiplicative group. That gives us phi twiddle. And the inversion, that was the new thing, inversion, which is going to be, maybe we'll get to the application of inversion today, maybe not. But this is important. The inversion, if I have the inverse, if I have the Mellin transform, then I multiply by the other character. I integrate ds over a vertical line like, sigma equals 2, real part of s equals 2, real part of s equals 2 or 10 or whatever. And then, of course, I divide by 2 pi I, and that will recover y. This is a function of y. The function of y is the original function p. Okay, so that's what we did. Then we talked about Hecke operators. Hecke operators on automorphic functions. On automorphic functions f, let's say in L2 of h mod gamma. What is the nth Hecke operator? So at z, so TNF is a function. What does it do at z? It takes f, evaluates it on mz, as m ranges over all matrices, integer matrices of determinant n. Delta n is m2z, such that the determinant is equal to capital N, modulo the action of SL2z itself. And then there was a normalizing factor. Did I tell you the normalizing factor or not?
Is it root n or something? Yeah, one over root n.
It's root n, of course. What else could it be? Yep, root n is the normalizing. Well, 1 over root n is the normalizing factor. And we had a fundamental domain for this this quotient, which meant that we could write this as sum over out. So we'll in this quotient, so delta n mod gamma looks like matrices of the form alpha 0 delta beta, where alpha times delta is n and beta runs mod delta. So this is alpha times delta is equal to n, a sum over beta mod delta, f of alpha z plus beta over delta. Okay, we saw that these things commute. We saw that they commute with the, well, it's a finite sum of actions of left multiplication by elements of SL2R. So it's going to commute, so the TNs commute with each other, and with the hyperbolic Laplacian, negative y squared, 2 derivatives in x plus 2 derivatives in y. So we can consider simultaneous eigenfunctions. So let phi in L2 of h mod gamma be a simultaneous eigenfunction, i.e., having well, it's an eigenfunction of all operators. So in particular, we have that delta phi is equal to lambda phi. Lambda is a quarter plus r squared. Maybe I'll say more about why. Let me say more about this later. And then Tn phi is lambda n phi. Okay, so there are some complex numbers, lambda and lambda n, so a sequence. In fact, these will all be self-adjoint operators, so these numbers are real. so that phi is simultaneously an eigenfunction of all of them. So far, so good? Yes, Nick.
Quick question, can you do something to make an L function like sum lambda n over n to the s? Is that Dirichlet series anything?
Yes, it is.
Because the usual L function, we get like the Fourier coefficients.
That's right.
Or am I forgetting things?
You ask that question in about 15 minutes.
Perfect, okay. Yeah, I forget how this works. I haven't done this since August.
That's good. Okay, so that means it won't be too boring.
Oh, no, not at all. I need a refresher on this.
Okay, good. Okay, so let's work out what the consequences of this process are. Okay, so the fact that we're an eigenfunction of the Laplacian means we have a Fourier expansion, and let's say we're even cuspidal. Let's say we're cuspidal. So so phi of z has an expansion. So let's say it's an even eigenfunction. So I can expand it as an times some Whittaker function, this solution to the differential equation, y to the 1/2 k I r coming from the eigenvalue of 2 pi n y with this k Bessel function, and then the e to the 2 pi I n x, right? That's our expansion. So that's what this implies. What does this imply? So let's see what Tn phi actually is. Tn phi of z. So it's this sum, 1 over root n, a sum over alpha times delta equals n, a sum over beta mod delta, and f, or phi evaluated at alpha z plus beta over delta. Now, what is the imaginary part? So now I have a sum over n, some coefficient an. What is the new imaginary part? Alpha, delta, and beta are all real. So if the imaginary part of z is y, what's the imaginary part of alpha z plus beta over delta?
Alpha over delta y?
Yeah, right? This is real, and it's just the only difference is, so I'm going to replace y by alpha over delta y to the 1/2 KIR 2 pi n alpha over delta y e to the 2 pi I n times the real part. And what is the real part?
Alpha x plus beta over delta.
Alpha x plus beta over delta. Pretty simple. Pretty simple stuff. Okay, what do you notice? Where do we have betas?
Only in the exponential.
Only in the exponential, and only in this part of the exponential.
This means we can evaluate it already.
Yes. So this thing, the blob, is what happens if n over delta is an integer?
Then this would give like n.
Exactly. Close.
Or delta.
Delta. They're delta terms, right? Then these terms are all the same.
Yeah.
And if otherwise,
It would be 0.
0. Okay, great. So let's continue the evaluation. I have 1 over n to the 1/2. I have a sum over alpha times delta equals n. And the only little n's that occur are those that are divisible by delta, that are multiples of delta. I have my a sub n, my alpha over delta to the 1/2, y to the 1/2, k IR of 2 pi n alpha over delta y, and e to the 2 pi I n alpha over delta x.
Wait, are we trying to verify like k will be like an eigenfunction for the Hecke operators?
I'm assuming that phi is an eigenfunction of all the Hecke operators. So I'm seeing what the consequences of that are. And at the moment, all I'm doing is putting in what the definition of the Hecke operator is. But now we had some simplifying things happen.
I see, I see.
Oh, and I missed the factor of delta. The only ends that occur are the ones that are 0 mod delta, and they come with a factor of delta. I'll just put it here. So far, so good. The only n's that occur are multiples of delta, so let me replace n by n times delta, so that this gets replaced by n greater than 1. Wherever I see n, I put an n times delta. Wherever I see n, I see an n times delta and n times delta. So far, so good.
What about the constant delta up front? Should that also become a, oh no, n became n delta, never mind.
Yep. That was just a constant. By the way, delta divided by root delta is root delta. And root delta times root alpha is root n. Oh, good. Good thing we had that normalizing factor. So this almost looks like a sum over just the expansion of phi itself, except at n alpha. So let me make a new change of variables. Let m be n alpha. Okay. So I'll write this as a sum over m. And then I have a sum over alpha times delta equals n. But actually, the only alphas that can arise are multiples of, are divisors of m. So alpha divides m. Okay. I have an a. So what is n times delta n is m over alpha. And delta, so if I multiply by delta, delta is big N over A, over alpha. Do you agree with that? Delta is big N over alpha. So if I multiply on this side by delta, I multiply by this side also by delta. So that's A sub m times n over alpha squared. That's this. So far, so good?
Yeah.
Then I have a root y, KIR of m, 2 pi m y, and e to the 2 pi I m x. Beautiful. On the other hand, I said that this was equal to lambda, just the constant lambda times phi. So this also has another expansion. This has another expansion as a series m greater than 1, lambda capital N, that constant lambda capital N, times am, times y to the 1/2, KIR, 2 pi my, e to the 2 pi I mx. If that's what it means to be an eigenfunction. So then what? Yeah. So I get an equality between the Fourier coefficients. These two series define the same function. Well, then the coefficients have to be the same.
And the Fourier coefficient's been unique. This depends on some decay conditions, right?
That's right. That's right.
Good
Which we
enough
have
decay.
because of the exponential decay of the K vessel.
Right. I just thought that was kind of funny that it doesn't actually come for free depending on how you converge.
Well, the way to access the Fourier, the nth Fourier coefficient is to integrate a function against e to the minus 2 pi I mx. So that integral, whether you do it from here or from here, has to have the same answer.
Yeah.
Okay, so what we've proved is a little lemma. Let's isolate this as a lemma, which is that the eigenvalue, the nth eigenvalue times the mth Fourier coefficient is a sum. Notice that there's no delta anymore. So this is just alpha dividing n and alpha dividing m. If alpha divides n and m, it divides the GCD of n and m. It divides both n and m of the coefficient a, m times n over alpha squared. That's a nice little lemma. So far, so good? Okay, what about when m equals 1? When m equals 1, this formula reads lambda n times a1. What are the possible divisors? What's the GCD of n and 1? 1. What are the possible values of alpha? Alpha can only be 1. So I get a 1 times n over 1 squared, an. This has some crazy consequences. This implies that if a1 equals 0, if this is equal to 0, then an is equal to 0 for all n, which means, of course, that phi is equal to 0. Conversely, if a1 is not equal to 0, well, then I can normalize, right? This eigenfunction is just a function up to normalization. I can divide by I can just normalize it. This is called Hecke normalized. Oh, I should have said what this is called. This phi is called a Hecke Mass cusp form. So being an eigenfunction of the Laplacian is the Mass, being an eigenfunction of all the Hecke operators is the Hecke, and being a cusp form is that a0 is 0.
Right.
Okay. So if a1 is not equal to 0, normalize. This is called Hecke normalize phi so that a1 is equal to 1. Just divide out by, that I can choose the vector up to constant. So I'll choose the constant so that a1 is equal to 1. Then lambda n is actually equal to an. This is crazy. These are eigenvalues of some operator. These are Fourier coefficients.
When it gets crazier.
So Nick, let me answer your question. Can we do something with the
This all rings a
eigenvalues?
bell. This
Sorry?
all rings a bell.
It all rings a bell, yes. So if we make an L function out of summing the eigenvalues over n to the s, well, that's the same thing as what we already did, which was taking the Fourier coefficients and making an L function. So yes, there is an L function with these eigenvalues. And it's the L function we've already seen. Okay, what about if n and m are co-prime? If n and m are co-prime, then their GCD is 1. So again, there's only one alpha. And we get that lambda n, also known as a capital N times am, is equal to a n times m divided by 1 squared.
Oh, would you look at that?
Yep. So the coefficients are multiplicative.
And that's all you need.
Well, that's all you need to be able to say that the series an over n to the s decomposes into infinite Euler product, 1 plus AP over p to the s plus AP squared over p to the 2s plus AP cubed over p to the 3s plus and so on.
Right, in this case, you have to like justify further why you can collapse this.
That's right. The question is, can we collapse this sum? Okay, is it clear why this is true? This is just you multiply all these things out and you get the prime factorization. Well, the prime power factorization. I can't control the primes individually yet. But decomposing any number into its prime powers, it occurs exactly once somewhere in this big product. Okay, and let's use this formula one more time. Let me do it here so I can see the formula. So it suffices to think about what happens to primes and prime powers. So what about a p times a p to some power L? So now there is a GCD. We have two terms. We have a term when alpha is equal to 1, and we have a term when alpha is equal to p. So alpha has to divide the GCD of p and p to the L. So there's a term alpha equals 1 and alpha equals p. Okay, when alpha equals 1, I just get a p. I just get like a completely multiplicative a p to the L plus 1. If there was no second term, that would be completely multiplicative, just like Dirichlet L functions are completely multiplicative. And this Euler factor would be a regular degree 1 Euler factor.
Right.
That's not what happens. We have the Hecke relation. And when alpha is equal to p, I get a p to the L plus 1 divided by p squared. So that's a p to the L minus 1. Does that make sense? Okay. So let's think about this big sum. Let's call it S. And actually, let's think about 1 over p to the s as, it'll be annoying to have all these p to the s. It's just some variable. Let's call it x. So I have 1 plus, let me leave a little room. 1 plus ap times x plus a p squared times x squared plus a p cubed times x cubed, and so on. Okay, so that's this series. I'm just setting x to be 1 over p to the s. Because that really is x squared, x cubed, and x to the 4th, and so on.
Instead of looking at this formally.
That's right. So if I multiply both sides by AP, well, let me keep the, hang on a second. Let me keep the definition of S before I do anything. And let me grab it, copy, paste. Okay, great. So now I can stare at it and I can manipulate it. So I'll multiply everything by AP. And actually, I'll also multiply it by x, AP times x. So this is times AP and times x. And actually, let me slide it over just a hair. Oh no. What was this?
That was the x to the 1. I don't
No,
know.
that was a P.
AP. That's what it was.
Very non-intuitive.
There we go.
Extremely.
Okay. All right. So let's see what this is. So I have I'm just going to multiply things out. I have an APX plus AP times AP. I know what that is. That's an AP squared plus an A1 times x squared. Right? I'm multiplying the AP by the AP, and my formula is that when you multiply AP by some power of AP, you get to multiply the powers and you get to multiply the powers and divide by p squared. I'm just following this recursion relation. Okay, so this is the x squared term. What's the x cubed term? I have an AP times an AP squared. So that's an AP AP cubed x cubed, but I also get an AP cubed over p squared, which is just AP x cubed. That's the x cubed term. Does everybody see that? The AP hits the AP squared, I get an AP cubed and an AP to the 1. Let's do one more term. What'll be the x to the 4th term?
AP to the 4 and AP squared.
Beautiful. Okay, very good. Let me add 1 to both sides. Because now I recognize the 1, the APX, the AP squared x squared, the AP cubed x cubed, the AP to the 4th x to the 4th, as just s itself. Then I see an A1 x squared and an AP x cubed. So let me do a double underline for these. And an AP squared x to the 4th. What does that add up to?
X squared times S.
It's x squared almost times s. I'm missing the first term.
Constant term or something.
Okay. That's it. I can solve for s. Okay, so I'm going to put all these things on the other side. I'm going to put a something I don't like. Oh, I'm sorry. That's what I don't like. A1 is 1. A1 is 1. Let me not delete it. Let me just cross it out as a 1. This is 1. So I do have a 1 and an AP and an AP squared. I don't need to subtract 1. I don't need to subtract 1. It is just x squared times s itself. Right? Does that make sense? And so now I can easily solve for s. S is equal to, if I move everything to one side, I get a 1. I get a minus APX. And I get a plus x squared. And then times s is equal to 1. So s is this thing inverse.
How do you know this thing is not 0?
It might be 0. I don't know yet that it's not 0. But let's look at it. Let's look at it here. So what this means is that the sum over this L function, this was the L function of phi at s, is also equal to this Euler product. We're gonna see in a second whether it could be 0 or could not be 0. This infinite product is a product of things like this, where x is replaced by p to the s. So that's 1 minus AP over p to the s plus 1 over p to the 2s inverse. Okay? And I can factor this quadratic polynomial. It's a quadratic polynomial in p to the minus s. If I factor that quadratic polynomial, I'll get 1 minus, let's say, some, I don't know, alpha p over p to the s inverse times 1 minus beta p over p to the s inverse, where this is just formally where alpha p times beta p will give me the coefficient in front of x squared, namely 1, and alpha p plus beta p will give me the coefficient in front of x with a minus sign, which I have a minus sign. So that coefficient is exactly AP. Okay, does that make sense? Now the APs are real. So the only way you get two numbers to multiply to be 1, whose sum is real, the fact that their product is 1 and their sum is real. Well, the fact that the sum is real means that their imaginary parts are the same. Imaginary parts are negative, are conjugate, right? So either imaginary parts are both 0, alpha p and beta p are both real, in which case, alpha p, here's 1, alpha p is going to be over here, beta p is going to be somewhere over here, beta p is 1 over alpha p. Or if they're complex, then they have to be complex conjugate. Alpha p is equal to beta p bar, and alpha p norm squared is 1. So that's this unit circle.
These AP are real because of the other side, right? The eigenvalues being
That's right.
real.
That's right. Real eigenvalues of the Hecke operators. Of the self-adjoint Hecke operators. So what's conjectured, so the Ramanujan conjecture in this setting, which is still not known, Ramanujan conjecture, generalized Ramanujan conjecture, is that only this happens, not this. This is the truth. Not this. So the eigenvalues are all on the unit circle. And what does that imply? That implies that AP in absolute value is bounded by something of size 1 plus something of size 1 is something of size 2. Okay, so let me go back to Andre's question about whether this thing can vanish. So if these things are of absolute value 1, if the alphas and the betas are of absolute value 1, then this thing indeed does not vanish, for the same reason that the zeta function doesn't vanish. In the region of absolute convergence, this is all for real part of S greater than 1.
Right, and there's no way for individual factors to cancel out or anything.
Right. It's actually very easy to prove. So a trivial, poor Hecke gets his proved the great theorem, but it's called the trivial bound. Trivial bound is that the ANs are bounded by n to the 1/2 times some constant. Yeah, let me prove that for you, because it's something very simple to prove. And this Ramanujan conjecture is still not known. Best known, again, this is the Kim-Sarnak bound, is that the APs are bounded by p to the 7/64.
This is for these Moss forms?
For Moss forms, yes. This is much more general than just for Moss forms of SL2Z. Yes, Nick.
For any AN, it has a factorization to alpha p and beta p both real. Like that always exists.
Alpha p and beta p both real?
Like that can always happen, right? Where they add to AP and multiply to 1.
The conjecture is that they're never real. So they're either on the real line or they're on the unit circle. The conjecture is the only time they're real is if they're both 1 or both -1. The conjecture is that they're always on the unit circle.
That factorization of AP equals alpha p beta p, is it unique?
In fact, it is, because
So if you give me a real number, there's only one way I can write it as a product like that.
yeah, up to symmetries, up to trivial symmetries.
Okay, but it's not, there'll never be 2 expansions, like one where they're both real, one where they're both in the unit circle. I can't.
Just let's see. If I take 7 and I want to write 7 as x plus y, where x times y is 1.
Yeah.
It's just a cosh, right? This is x plus 1 over x. So that's a cosh, which is invertible.
Gosh, which is what?
which is invertible.
Right.
The cosh function is invertible, as opposed to 1.5. If I write 1.5 as x plus 1 over x, that is not a value of cosh, because cosh is always at least, well, cosh is always at least 1, but this is twice cosh. This is 2 times cosh of log x.
Okay, so for large enough x,
Greater than 2. Greater than 2 or less than 2 is exactly the splitting point between cosh and cos. This is going to be twice cos x.
I see.
So just like the cosine function, a cos log x, whatever, log x.
Okay, so the conjecture really isn't, do there exist alpha p, beta p on the unit circle satisfying that? It's really which is it?
Yes,
It's most definitely one of, it's only one of them.
it's
Okay.
only one of them. These are the only possible things that can happen. And they completely depend on whether this AP is greater than 2 or less than 2.
Right, okay.
So cosine parametrizes the circle, cosh parametrizes the hyperbola,
Right.
and you can only be on one or the other. And the split is exactly whether this number, which is twice cosh, is greater than 2 or less than 2. In which case, this cosine is cosh. Either cosh is an imaginary cosine or cosine is an imaginary cosh. Right.
Right.
Cosh
Okay.
x is cosine of ix.
Right. Something like that. Yeah,
Something like that.
that's probably it.
I think something exactly like that.
That's probably it. Okay.
So that's exactly what's going on. Depending on the value, the size of this AP determines whether you're here or here.
Okay.
And
Thank
the
you.
conjecture is you're always here. You're always on the circle. You're never on the hyperbola. There's
Right.
never a cosh here. This value is always at most 2. And what we currently know is that, well, it might not be always 2, but at least it's no bigger than some, that you're restricted how bad the hyperbola can be. You can easily restrict to this. So there's a much worse restriction on how far along the hyperbola you can be.
I actually cannot read it. This trivial bound, can you?
The trivial bound is some constant times root n. Some constant times n to the 1/2.
Thank you.
Yes.
I have a question about the recursive relation we got on the coefficients.
Yes.
Like, I mean, we didn't really use much in a sense, right? We just did it for like 1 and we did it for like.
In
A
one
prime
sense, we didn't
and
use
prime?
much, but in another sense, we used it for all. So this one recurrence relation captures the full depth of the Hecke relation.
Isn't that like really strange?
No, the Hecke relation really is a second order recursive relation, which is why we get a degree 2 L function, which is why we get this degree 2 Euler product. There are 2 factors of p to the minus s. And it captures the full Hecke relation is right here, and because it's a you see, it looks like it's more complicated, but it's actually a quadratic relation. So if you have a quadratic, if you capture the quadricity or something of it, then you've captured everything.
Okay, so
And when you go to GLN, it'll be degree n. It'll be a degree n recurrence relation, and you get a degree n Euler product.
Interesting. And will you be able to sort of identify it in this way, doing like power series manipulations?
That's right. That's right. It gets a little more complicated, but it's a similar operation. And the conjecture is that all of the APs, so you get a degree n, you get a degree n series here, which is a little complicated to describe because there's some funny things that happen in higher rank that we haven't seen yet. But basically you get a bunch of coefficients and they can all be identified. You factor this thing and you get a bunch of APs up to the symmetric group on the roots. And there's a little bit of not Galois theory, it's sort of baby Galois theory, that the products of the roots will be 1 and the sum of the roots will be AP, but the sum of the squares of the roots will be one of the other coefficients and so on, that you get an nth degree polynomial in p to the minus s here. And then the conjecture is that all of the coefficients are on the unit circle. All of the Satake parameters, these things are Satake parameters, Langland's Satake parameters, these alphas and betas. Thinking about the roots, the fact that you think about the roots and not about the Fourier series, that's kind of the big insight. So these are the Langland's Satake parameters.
That's where you can look at it with a Galois perspective.
Right.
Oh, that's really it must have been like amazing to realize this, I guess.
That's Langland's Euler products book is the realization of the importance of the Satake parameters over the Fourier coefficients. It looks like the Fourier coefficients give you what you need, but it's a red herring. Okay, shall I prove the trivial bound for you? I had a bunch of other things I was going to do today, but let's do the trivial bound because I think it's good to be able to see just how to get your hands on some kind of polynomial. If you don't have any polynomial bound, you're in trouble because you can't even form a series. Where does a series even converge? You need some bound to say that the series converges somewhere. If these things really are of size 1, then it converges. So actually, the fact that I wrote 1 here is, let's be a little safe. I don't know this yet. The Ramanujan conjecture would say that yes, this converges all the way down to 1. But we don't even know that at the moment. That the L series as stated.
And then like asking for real of s to be, some number, then guarantees this won't vanish, right? And then the whole thing, it works.
Where the Euler product converges absolutely, it can only vanish if one of the terms vanishes. But you just stare at the terms and you see that p to the s, when s is large, is going to be too small relative to the size of the AP.
Or p to minus s.
P to the minus s, yes.
Yeah. Now that makes
Just
sense.
like for Dirichlet functions.
Right, it's just having a half plane convergence, right? So.
Exactly. So let's see how to get the trivial bound. Okay, this is very simple. So you have phi of x plus iy. And how do I get the nth Fourier coefficient? What is an? So I'll take e to the minus 2 pi n x, and I'll integrate that dx from 0 to 1. And what will I get? I will get an y to the 1/2 kir of 2 pi ny. Right? That's exactly the nth Fourier coefficient for any value of y. This is what I get. Okay, but let's think about the function phi. So I'm going to take absolute values. Let's think about the function phi. It has some values in this bulk part. It's going to 0 at infinity. So phi is just absolutely bounded, and it's automorphic. It takes the same values all over on the upper half plane.
Yeah.
So phi is just bounded. Phi is just bounded by some constant for all z on all z and h.
And again, when you have like a cusp form, right, then like you leverage this as well, right?
I'm already assuming it's a cusp form, but actually it doesn't have to be in what I'm saying here. Even if it's just a modular form, even if it's just even if it has a constant term, it approaches that constant term at infinity.
Oh, I guess I meant for modular forms.
Modular forms, you have to be a little bit careful in this argument. There's a slight modification, but yes, it's basically the same argument.
Right, you need like the cusp, the fact that it's cusp to like make it go through like this.
Just that it's holomorphic at infinity. It doesn't have to vanish at infinity.
I see. Okay.
But you have to do something here to make it automorphic, to be able to say that you get something that's bounded really on the entire upper half plane, because it changes. Unlike an automorphic form, a modular form changes as you move from fundamental domain to fundamental domain.
And then you multiply it by the imaginary part or whatnot, right?
Right, you have to multiply by y to a power here. Yeah, that's right. That's how to fix this.
Okay, cool.
Okay, so I have this, but just look at this. This is bounded by a constant. This is bounded by 1. I'm integrating over 1. So this product is bounded by a constant. So I know that an is bounded by y to the minus 1/2 And I have to divide by this k Bessel function, KIR of 2 pi n y. Now I told you that the k Bessel function decays exponentially. This k decays exponentially.
Yeah, so it sort of grows exponentially when you put it like that.
This is very bad. This grows exponentially.
Yeah.
So 1 over k grows exponentially.
Yeah, but why is that our disposal?
You still have this, yeah, the y. Wait, what does the r depend on?
The r is the eigenvalue. So I have a fixed phi, it has a fixed eigenvalue r. The Laplace eigenvalue is a quarter plus r squared. I want to explain that also.
And so then, yeah, it depends on your choice of y, as Nick was saying.
Yeah.
Exactly. If I just do this naively, it looks, if I just set y equal to 1, what is y equal to 1? It means I'm integrating at height 1 over this horocycle. Right? That's what this integral is doing. I'm integrating the function against the character at height 1. That would give me a 1 here, but it would give me a e to the n. If I set y equal to 1, I get that the an is bounded by some constant times e to some constant to the n, which would give me then the L series, L of phi s, converges nowhere. I have no region of convergence. I'm summing an over n to the s, with the an's growing exponentially. For what values of s can I get absolute convergence on them? Nothing. Okay, so the key idea. What's the key idea?
1 over n.
Take a low-lying horocycle. This is true for any y. Any y, I have this identity. So set y equal to 1 over n. I have to take a horocycle at exactly the right height. This is the height y equals 1 over n. And then what I get is that an is bounded by, I missed the constant, here's the constant. A constant, y is equal to 1 over n, I have y to the minus a half, that's my n to the 1/2. And now I'm dividing by k IR of 2 pi, which is also a constant. The constant depends on phi.
Like this sort of choice of 1 over n is gonna end up being like tight, right?
It's going to be tight in this argument,
In this
in
argument,
this trivial argument.
which is it's nice, I guess.
Yes. Okay, so that's the trivial bound. That's this trivial bound.
Wait, I didn't, sorry to like go back again. I didn't really understand the discussion about the hyperbola and the circle for like the Satake parameters.
Yeah, all I'm saying is that if let's say AP was 7, then I'm saying that alpha p plus beta p is 7, so that's x plus y is 7, but alpha p times beta p is 1, that's x plus y is 1. So if I just say y is equal to 1 over x, this is x plus 1 over x. Has to be 7. The solution to that is cosh, is the inverse of the cosh function. X plus 1 over x is like twice cosh of log x.
Okay.
Whereas if it was not 7, but something less than 2, 1.5, some random number, x plus 1 over x is also twice cosine of log, well, ix, I guess. So whether you get a cosh or a cosine solution depends on whether the number you're trying to represent as x plus y with x times y equals 1, whether this number is greater than 2 in absolute value or less than 2 in absolute value.
And you're saying that like once it's true for one of the p's, it's just going to be true for all of them?
No, the conjecture is that for all p, the conjecture is for all p, the AP is at most 2. For every single p, the p is on this circle. The alpha p is and the beta p is on this circle, and not a pair of real numbers with one being of size 7, one being of size 1/7.
Right, so you're sort of ending up in the cosine case.
Exactly. It should always be in the cosine. The cosine should be what's always happening, not the cosh.
And you're saying like where these happen is like a disjoint or almost disjoint?
Almost disjoint, yes. Except when AP is exactly equal to 2.
Right.
It's either or, but including the cosine. I mean, what I don't want is anything on this part of the spectrum.
When you're saying there's a conjecture, so we don't know this?
We don't know this. We do know it for modular forms, thanks to Deline.
Right, I mean, that's just delete. Yeah.
We do not know this from Moss forms. We have bounds that are much better than the bounds we just proved, which are the trivial bound.
Oh,
And then when did Kim and Sarnak do this?
Oh, this is late 90s, early 2000s, maybe 02 or something, 03.
Interesting.
Does anybody know? Should I try to put a number here? I'll put 02, but I think it's not quite right.
So when you worked with Sarnak, this has been like, you know, within like recent history in a sense.
Sure. Yeah. Yeah. Kim had just proved this symmetric fourth functoriality.
That's pretty cool.
Yeah. Okay. Let me justify. Let's see. I have two things I wanted to tell you. One is a modification of this for modular forms, just to give you some hint as to what to do there. And another is a little discussion of the Laplacian. I think I'd rather do the discussion of the Laplacian because let's stay in the automorphic world for just another. I think maybe I can do both. Maybe I can do both. Let's stay in the automorphic world for just another minute. So I proved a trivial bound for the Fourier coefficients. Let me prove a trivial bound for the eigenvalue. And the reason I want to, these look like different things and the arguments will be rather different. But from the point of view of representation theory, they're one and the same. From the point of view of representation theory, this lambda, I should call lambda infinity, and these will be the different TPs.
I think 2003 with the Google search.
2003, okay, thanks.
It's the functoriality for the exterior square of GL4 and the symmetric fourth of GL2
Beautiful.
by Kim, Krishnan, and Sarnak.
Okay.
If that's the
Right,
right
there's
one.
another appendix with, it's really, it's Kim's paper with some appendices.
Sure.
Okay. So they look different. Well, even adelically, they look a little different, right? What does it mean to be smooth? Well, you're smooth in the infinite place, and then you're compactly supported and locally constant in the p-adic places. But actually, these two things are all the same. So let me give you let me justify writing this as a quarter plus r squared. In particular, that this is bigger than a quarter, as long as r is real. In other words, as long as IR is imaginary, it's purely imaginary. So in fact, let me state the Selberg 1/4 conjecture. So this is an important, the analog, the infinite analog of Ramanujan conjecture is the Selberg, the celebrated Selberg 1/4 conjecture, which states the following: let gamma be a congruence group, be a congruence group that is, gamma contains as a subgroup one of the principal congruence principal, let's call this gamma q, gamma n, whatever. Gamma q is the principal congruence group of level q, which means this is the kernel of the map from SL2Z to SL2 Z mod P, Z mod Q, Z mod QZ. Okay, we talked about why this map is onto, right? That SL2Z surjects onto SL2 Z mod Q Z. That we can lift any element here we talked about lifting elements in SL2Z mod P to elements of SL2Z, which we can't do for geo. The kernel, what does it mean to be in the kernel? It means matrices, A, B, C, D, gamma, that are congruent to the identity mod Q. That's all. Mod Q. Gamma in SL2Z. Okay, writing it as a kernel means you can immediately see that it's a normal subgroup of SL2Z, which is important for some applications. Okay, so a congruence group means you contain some principal congruence group.
Sometimes they require zero only in the lower lower left corner.
Right, so there are different congruence groups. This is the principal congruence group. Then there's gamma 1 of Q, which is the gamma is upper triangular.
I see.
Mod Q. And then there's gamma, I'm sorry, that's gamma 0. Gamma 1 is that you're unipotent mod Q. So this is identity mod Q, or just unipotent mod Q, or gamma 0, gamma naught of Q, which is that gamma is upper triangular mod Q. These are the standard various congruent subgroups. Notice that this one contains the principal one. If you're the identity, then you certainly have a 0 in the C entry.
Where did this notation come from?
It's been around forever. I assume Selberg, but I don't know that for a fact.
And with these, like, I vaguely remember with some sort of converse theorems or stuff like that, that you'd end up needing these.
That's right. That's exactly right. We're going to need, especially this one for Bayes' converse theorem, which I did promise. Which is also why I wanted to remind you about Mellin transforms and inverses, but I might not get there today. Okay, so here's a Selberg 1/4 conjecture. So if you have a congruence group, and let's say you have, if phi is in L2 of H mod your congruence group, you can think about principal ones or one of these, doesn't matter. And delta phi is lambda phi, and phi is not a constant. Then the conjecture is, this is the Selberg 1/4 conjecture. The conjecture is that this eigenvalue is at least a quarter.
I mean, that gives a reason to normalize them the way we do.
You mean that I put a minus sign here? Yes.
Oh, I mean, not only that, like you write the eigenvalue as 1/4 plus, like.
Yes. Yes. In fact, the normalization, Selberg already observed this. The good normalization is to write lambda as s times 1 minus s. And so the fact that lambda is positive, again, tells us we have two options for s. S times 1 minus s is a parabola, like the graph of s as a real valued. If s is a real number, and this is lambda as a function of s, a quadratic polynomial in s. It has a 0 at 0, it has a 0 at 1, and it's a negative parabola. So it's something like this. It has a maximum value at s equals a half of 1/4. If s is real, this is if s is real.
So the idea is
S-
take it to the complexes and like see that,
Yep. The
The-
only other option is that s and 1 minus s are conjugate. Or s, so the s is 1/2 plus ir, and in which case 1 minus s is also 1/2 minus ir, and s times 1 minus s is a quarter plus r squared. So hopefully you see the analog between these two possibilities and what we just discussed for the Ramanujan conjecture. And so Selberg's conjecture, this is Selberg's 1/4 conjecture, is that only this happens. Only the complex conjugate situation happens. This situation does not happen.
Wait, but I guess I'm confused about why the real case would be messing things up.
I haven't explained it yet.
Oh, okay.
I haven't explained why this messes things up. These are called exceptional eigenvalues. So if you look at the spectrum of the Laplacian on one of these congruence groups, we know that the spectrum meaning set of eigenvalues. Let's take that as our working definition. Here's the number. Here's this magical number 1/4, and the conjecture is that all of the eigenvalues happen here. We have an eigenvalue at 0. Lambda equals 0 is the eigenvalue that corresponds to the constant function.
Right.
So if phi isn't the constant function, the claim, so it turns out that there's continuous spectrum above 1/4 that's spanned by the Eisenstein series. I realize I'm just saying words right now, but the question is about these discrete eigenvalues that come with L2 eigenfunctions. And if they occur, they'll occur embedded in the continuous spectrum. And the conjecture is that they never get beyond 1/4. So this is called the exceptional spectrum. Between 0 and 1/4, if there are any eigenvalues here, that's called the exceptional spectrum.
Just thought there's nothing there.
Spectrum, the conjecture is that there's nothing there for congruence groups. In the same paper where Selberg stated the 1/4 conjecture, he shows that you have finite index subgroups of SL2Z, non-congruent subgroups, which do have eigenvalues as close to 0 as you want.
Well,
Okay.
wait, so you said subgroups of
Yeah.
SL2 that aren't congruents.
That's right.
Main comment.
There exist subgroups, in fact, the sequence of subgroups of SL2Z of finite index such that, let's call this lambda 1. Lambda 1 is the first eigenvalue above lambda 0. There's always an eigenvalue at lambda 0. They're finite index subgroups. So the constant function is L2. Such that lambda 1 goes to 0.
So I guess like that means containing a congruent subgroup is special.
Yes. And this is just a rank 1 phenomenon. So Margulis famously proved arithmeticity that any, let me put an aside here. A famous theorem of Margulis arithmeticity is that if G is a higher rank, if G is, so in this case, G is SL2, a higher rank, a rank greater than 1, higher rank group. And well, this isn't quite what I want to say. And gamma is a lattice. Gamma is gamma is a lattice in GR. Then gamma is arithmetic. Yeah, this isn't really what I want to. There are also non-arithmetic. You see, just the fact that you have elements, these are matrices in SL2Z, so all of their elements are integral. They're already arithmetic. This is really an aside. This is a far aside. Never mind this aside. It's not that it's false, but it's not where I wanted to go with this discussion.
Wait, and then when you say spectrum is continuous, you sort of mean like, in this case, every value above 1/4 is represented?
So every value above 1/4 occurs in the spectrum, but not because it occurs with an eigenfunction.
Okay, this is some weird stuff happening with it.
Yes. Yeah, let me not go into, so it's parametrized by the Eisenstein series. This was already understood by Selberg.
Right. This is sort of what you were saying, that when you decompose, right, you're not going to get functions that are exactly like L2.
That's right. That's right. The Eisenstein series are almost L2, just like the on the real line, Fourier analysis and the reals. You have e to the 2 pi I xc is a function which is not an L2, but does occur in the decomposition of L2.
Right.
And the spectrum is continuous, purely continuous. Unlike the circle, where the spectrum is purely discrete, e to the 2 pi I n x has discrete spectrum. Let me, since time is running, let me, I want to say the congruence subgroup property here. Okay, let me move off of higher rank and go back to what's happening here. So let me state a theorem. For SL2Z, we can prove Selberg's conjecture. Theorem, Selberg 1/4 holds for gamma equal to SL2Z. This is also a trivial argument.
So this is again like modular forms and the
Well, modular forms don't have Laplace eigenvalues.
I mean, this is like, I guess what I was trying to say is this is the case that we were studying, the gamma equals SL to.
Yes.
Z.
Yeah. So for SL2Z, i.e., phi is a Moss form for SL2Z. Moss form for SL2Z implies lambda is at least 1/4. So let's see why that's true. I think I can do this in 7 minutes. Okay, proof. How do you access any of these things? It's with the Laplacian. So Laplacian phi, inner product phi. Let's try to understand what this is. So the inner product is, of course, the inner product over the fundamental domain. So I have some fundamental domain D. D is a domain for upper half plane mod SL2Z. And then I have Laplacian, which is negative y squared, 2 derivatives in x plus 2 derivatives in y, applied to phi. And then I multiply by phi bar, and then I integrate dx dy over y squared. Okay. So the y squared from the Laplacian exactly cancels the y squared from the Haar measure, or from the invariant measure. And if I integrate by parts, so integrate by parts, if I do it once, then the boundary values will all exactly cancel off. The minus sign, I'm integrating by parts. So that's exactly why I'll get a plus sign here. I get an integral over the fundamental domain. And I'll move one of the dx integrals over here, and I'll move one of the dy integrals over here. And I'll get dx plus dy, in other words, grad phi, norm squared. Dx dy, not y squared.
But you can integrate by parts like that?
Yeah, I'm integrating by parts with dx. I mean, these are 2 different sums. Separate this into 2 sums. On one sum, integrate dx. I integrate this, I differentiate this with respect to x. On the other sum, I integrate this with respect to y, differentiate that with respect to y. And then put them back together. You'll see that this is exactly what you get.
Oh, you're saying that this sort of like splits into like 2.
Yeah,
They're like kind of independent.
that's right.
Okay.
Okay. So far, so good. Which, by the way, tells us the notice that this is non-negative. And if phi is an eigenfunction, then this is equal to lambda phi. So this is lambda times norm phi squared. Does this make sense?
Oh, sorry, can you say the last part again?
So if phi is a Moss form, that means it's an eigenfunction of the Laplacian with eigenvalue lambda.
Right.
So delta phi is lambda phi. Lambda pulls out as a constant, and I get inner product of phi with itself. That's norm phi squared.
Yeah.
So that already tells us that, I mean, this, maybe I didn't say why the Laplacian was positive definite. Here's the positive definiteness. That means lambda is bigger than 0. We want much more. We want lambda bigger than 1/4.
Right.
Okay. I should have said cusp, by the way. Cusp form.
Because you're using here this phi like is bounded by a constant.
Whatever it is, whatever the norm phi squared is, this is non-negative. and on the other side, I have that it's non-negative. So lambda times something non-negative is bigger than 0.
Right, but if you have a number on the other side, then you'll have to understand phi.
No, because I'm saying something weak. I'm saying lambda times norm phi squared is positive.
Right, I mean, like when you try to like replace that zero on the other side for something better, then you'll have to understand phi better.
That's right. That's right. I have to do something non-trivial here. Okay. You're absolutely right. Yeah. I'm sorry. This is completely trivial. This is going to be non-trivial. Slightly
Right.
non-trivial. And it's going to fundamentally use the fundamental domain. So here's D. Here's my choice of D, the standard one. This is an integral over D. Now, if I take the integral over this region, I also get the same integral, right? Phi is invariant. Phi doesn't care which domain you chose.
Right. And that's just by like inversion, right? Is essentially what you're doing.
That's right. That's right. This is SD, where
Yes.
S is this 0, 1, negative 1, 0. So I'll double this integral and I'll have it. So if I double the integral and I have it, I still get the same thing. And then instead of integrating over the whole doubled integral, I'll just integrate over this part of the doubled integral. So that's an integral over y going from √3/2, that's this height, to infinity.
Wait,
And
which
x
integral are we looking at specifically?
The original integral was over D.
We're looking at this one, right? Where everything is positive.
Where everything's positive. Yeah, but now forget this. Forget this. Go back to this integral.
Right, but what I mean is that you can only write the greater equals because you know that it's positive.
Everything's
everywhere.
positive. Yep, absolutely. Absolutely.
Okay.
That's essential. Yes, everything's positive. Okay. So I'm gonna double the integral and have the integral, and then I'll forget a whole bunch of the integral. I'll only take the part from √3/2 and y up to infinity and minus a half in x of the same thing. Grad phi squared dx dy. No problem there. Now let's think about that. Remember what phi is. Phi of x plus iy is a sum. Again, let's say it's even. Come on. Let's say it's even. Some coefficients an, cusp form. This is essential that it's a cusp form. An times y to the 1/2. It doesn't matter what this function is. Actually, it could be. Let me not confuse you by giving it a new name. It's called a Whittaker function. But whatever, we know what it is, so let's just write it out. E to the 2 pi I n x. I want to apply the grad operator to this. Okay, so if I differentiate in x, what happens when I differentiate in x? I get a factor of 2 pi I n comes down. What happens if I differentiate in y? If I differentiate in y, I get whatever this is, d dy of this y to the 1/2 kir 2 pi ny. Whatever that is, I don't even care what that is. So far, so good?
Sure.
Okay. Let's remember Parseval's identity for this inside thing. Whenever I have a Fourier series for a function, if I integrate the norm squared of that function over the period, it's the same as summing. So if I take the absolute value squared of everything and I integrate dx from 0, 1, or whatever, minus a half, this will be just the integral, this will be the sum, n greater than 1, an squared of this thing squared, okay? Now let's think about this for a second. This is real, this is imaginary. So actually I get d dy of all of this stuff, which doesn't actually matter, squared plus this part squared. So this is the real part squared plus the imaginary part squared, which is 4 pi squared n squared times the same y to the 1/2 KIR of 2 pi ny squared. Okay, so this is just Parseval.
Wait, which were the real and imaginary parts come from again?
So what I'm saying is I'm taking the I had this grad phi, which if you look at the partial derivatives, one derivative hits the x, one derivative hits the y.
Yeah.
And then when it hits the x, you don't even have to think of it this way. But when it hits the x, it has this imaginary part. Everything else is real. This is real. This is real. This is real, and that's imaginary.
I can't see where you're pointing the cursor.
Oh.
It's like
Oh.
when you write, it's visible, but like
Oh no. How about this? Is it visible now?
Or
Is it visible now?
Can you write something?
oh, there you go. Now,
Okay.
Oh
it's
no.
not-
So every time I move the cursor, you can't actually see?
yeah, that's correct.
Oh, that's so awful. Okay. I'm sorry. I wish you guys had told me earlier. I would switch to this thing. Okay. This thing is real.
Yeah, you're
This thing
saying
is also
visible.
real, but it
You're
has
saying
an imaginary. Sorry, say it
Right. If
again.
you expand it- oh, that if you expand it out, you'll see that it's real. Is sort of what you're saying.
Yeah, I'm just looking at the two terms here. So let me finish up, and since we're already out of time, this part it's not going to matter actually. We have this part here, and then we have this part here, and that's the sum of squares. And now I'm going to do something entirely trivial. I'm going to put a less than sign, and I'm going to drop a bunch of terms. I'm going to drop all of this, and n is at least 1, so I'm going to drop this also.
So you're just dropping positive things.
I'm just dropping positive things. Okay, so if we go back to this integral, I'm dropping positive things. If we go back to this integral, yeah. If we go back to this integral, I'm dropping a bunch of positive things. I have this factor of 1/2. I'm integrating from √3/2 to infinity. And what is this? I have a an squared, a sum over n greater than x, an squared, and then a √y KIR of 2 pi ny squared dx dy, right?
Yep.
I want to put in an over y squared. I want to multiply by y squared and divide by y squared. No, I want to leave the y in here. I'm going to leave the y inside and leave the y squared alone. Let's leave the y squared alone. This is what happens when you rush when you're near the end of when you're out of time. We're almost there. We're very, very close. I need the y squared here to be able to say that this is related to the L2 norm of the function itself. And then there are these constant. We got this factor of 4 pi squared coming out, and 4 pi squared is way bigger than a quarter. So we're going to get a lower bound that's way better than the proper lower bound. Let me not. We need like 5 more technical minutes, which is not a good thing to do when you're already 5 minutes past. So to be continued. We're going to pick up here on Friday. To be continued. ... We're almost there.
Sure.
I don't want to keep you past time, but it is a very simple argument. I thought I could do it in the time we had, but I'm not quite there. The point is we'll get a lambda norm phi squared, and this will again be related to norm phi squared because it almost is norm phi squared. I mean the dx, there is no dx here. I'm going to put in a dx in a second by using Parseval back and reverse. So, all right, to be continued.